Thank you, Jean-Bredi, and also thank you for the organizers for the invitation. So I will today talk mostly about one paper that is also written here. It's co-authored also by Uriel Frisch, who you pretty all of you, I assume, know very well, and also Oliver Hahn. He is also based here in Vienna at the math department and astrophysics department.
You haven't shared your screen. I mean, it was shared. It's no longer shared.
Oh, let me rectify that. Yeah.
Unless it's intentional.
No.
Yeah, now it's all visible, and your mouse is.
Can you see it now?
Well, the cursor is visible as well. Yeah.
Can you see me now? Can you see the screen?
We can see the screen. We can see the slides. We can see you, and we can see the cursor. So everything's good.
Okay, perfect. Okay, now we are ready to set up. Yeah. So I was really just like highlighting this paper here and the co-authors at this stage. And before I even give you like an outlook, what I want to talk today about, I want to give you like rather a context and overview. Might be some boring for some of you, but nevertheless, I want to do it. So the Burger's equation, as many of you know, is quite a prototype of a problem in fluid mechanics. Can be used for as a reduced model for turbulence, gas dynamics. Also in cosmology, for example, it has important applications. And the one space dimensional version of in a zero viscosity case of the Burger's equation is written here. And some solutions are very well known for decades. For example, the solution with non-vanishing viscosity, which is basically obtained by exploiting the Hopf-Kohl transformation. And there's also the well-known solution when you take the limit of the viscosity going to zero. That is a very interesting paper if you are interested in that details. And lastly, which is essentially the main attention of today's talk, is the vanishing viscosity limit, which is for that the solution exists when you work in Lagrangian coordinates. And that solution is valid until the first real singularity, which is which I defined as the pre-shock. Okay, so so I work specifically on this vanishing viscosity limit, not limit, but the case, yeah, and work also mostly in Eulerian coordinates. So this is the equation that I will mostly focus about. Now, I will also focus first on very early time solutions. So until the pre-shock time. So you might be wondered why is this so interesting. So, well, I of course had an angle before I started this project that I will come back to at the end of the talk. So I found something essentially that was relevant in cosmology, and then it tracked my attention back to the prototype equation where the same issue also appeared. So, but nevertheless, there are of course many reasons why one should investigate the regime until the first singularity appears. For example, if one wants to investigate numerical simulations of the Burger's equation or of Euler equation, Navier-Stokes, and many of these simulation techniques employ Eulerian coordinates. And sometimes one has to live with the consequences while working with Eulerian coordinates. This is what essentially, this my understanding is that the advection problem is not optimally resolved in Eulerian coordinates, typically, not always. And as a consequence, one has to be basically living with some issues like Tigers that have been investigated, I think at first in much detail in this paper by Jean-Bredi and co-authors, but also of incompressible Euler flows. There have been a couple of very interesting papers on this issue. But again, my angle is slightly different today, so I will try to come from another point of view. And again, why until pre-shock? Because if you, for example, want to investigate the blow-up problem for incompressible Euler flow, you need high accuracy before and until the first real singularity. if there is a blow up, basically. And I claim at least some knowledge of the overall singular landscape can be very helpful if you know this information. And lastly, I will also come back to this at the end of the talk. So if you know where the singularities are located and you know the type of singularities, this can also give improved theoretical predictions. And I will come back to this later during the talk. So the outline of today's talk is I will first show you essentially the complex time singularities that we have investigated in the inviscid Burgers equation. And I will go in some pedagogical details, especially to the first point, but also will give a lot of details about the second point here. So in a sense, there are two complementary ways how to analyze complex time singularities. Or there are many more, but we have investigated these two here. And so what we will see shortly is that for certain implementations, in our case, also a Lagrangian coordinates approach for the inviscid Burgers, we observe a certain resonant behavior that is initially localized in space, it's spatial locations, but at later times it takes over the whole space. So essentially there's some completely loss of information happening. And these resonances, they are related to the Tyger phenomena that has been reported for now 11, 12 years in Galerkin truncated implementations of inviscid fluids. So there's some relation to this issue. And then also I will show you what you can do actually to get rid of these early time Tigers. One of the approaches is essentially inspired by a recent paper where also Ray and Murugan were involved. And this is essentially an adaptation of that method that removes certain Fourier modes and that basically cures the problem to some extent. And the other method is essentially something that we came up and it basically attempts an iterative UV completion. And I will tell in detail what this means, of course. Yeah. And lastly, I will also give some application how one actually can exploit this singular knowledge to get better theoretical predictions. So the basic setup is, again, the inviscid Burgers equation. And by no means I'm encouraged to solve the inviscid Burgers equation by using a time Taylor series. But if you do so, you actually have a very sturdy tool at hand that can help you to get or retrieve information about the singularities. So my angle is here that let's use such a simple Taylor series to precisely gain knowledge about singular structure. And to do so, it's actually fairly straightforward. One uses an ansatz and hope that it doesn't lead to inconsistencies when plugging it into the equation 1. And it does not. So there are actually simple recursive relations one can retrieve by using this ansatz into equation 1. These are written here. So interestingly, once you specify the initial data, which I call U0, you can iteratively and explicitly calculate these Taylor coefficients at arbitrary Hall orders. And let's focus first on the very simple single mode initial data. So let's say that U0 is just minus sine x, and then you can use like a computer algebra program to calculate the coefficients explicitly. So we have done actually little numerics in this project here, so because we wanted to really boil down what we can do in a practical manner, analytical manner. So the solutions that I'll show you later on are really based on these analytic results here. So there's not much space for numerical errors if you're worried about that. And one interesting feature of these Taylor coefficients is the following. If you start, as in the present case, with a single mode initial data and say it has a Fourier coefficient k equal to unity, as written here, basically, and you see that higher order Taylor coefficients basically contain multiples of the initial data. So at the next order, it contains 2, 3, 4, and so on. It also will contain several other modes that are essentially below n+1. But the point I want to raise here is essentially that you get at fixed Taylor series truncation, so you don't go here to infinity, but to capital N, for example, then your Taylor series solution is naturally also band limited, because you can represent these signs here in terms of a Fourier basis, and then you will see essentially that the largest Fourier mode is essentially plus minus n+1. So this band limitation plays also quite an important role for triggering Tigers, as we'll see shortly. So, and here are some Tigers. Basically, let's just focus on this Taylor truncated velocity that I define with this kind of operator here. So that really just selects the first n Taylor coefficients, capital N Taylor coefficients, and as before, the initial data here. So, and I show you essentially the velocity, the Taylor truncated velocity for 3 different times. So for the present time, we know by exploiting the Lagrangian coordinate solution that the pre-shock occurs at t = unity. So we are actually quite far away from that still here. What you can see is that at these kind of very early time, you see that the Taylor series appears to converge nicely. But suddenly, slightly later, you see some resonant behavior. And if you go to later times, it vastly amplifies. So this is what I meant earlier, that you get some resonant behavior that is initially localized. But what you see here is that the amplitude and the width of these resonances increases drastically. Yeah? So if I would show you here also the result at pre-shock time, you would see nothing here, because the whole figure would be completely green, so completely thermalized, basically. So now, what's happening here? I mean, first of all, from a theory point of view, if you work with Taylor series, you would expect that the Taylor series struggles somewhere near the pre-shock, because this is kind of the interesting regime that might be tricky to resolve by using perturbative methods or whatever methods you have. But we get these really weird features at seemingly boring locations. And as we will see, this is very similar to what has been observed in these Galerkin truncated implementations of inviscid burgers. And the origin or the true source of these resonances here is essentially just loss of time analyticity. Yeah? Okay, so this now starts the pedagogical parts. So this is essentially, some parts are mathematics 101, I would say, but I don't mean this disrespectful, because it's for many of you, you might have not had contact with this for many years. And so I think it's good to get it quickly freshening up, and to also get hopefully some intuition what's happening. So there's the initial attempt that actually we tried as well before we when we saw these resonances occurring. Let's see what actually happens with the rays of convergence of your time Taylor series. So as you can also see here, essentially it's an expansion around the origin in time here. And then we know essentially that we could in principle perform the ratio test that could give you the rays of convergence if the involved limit exists. This is very crucial, because it doesn't in our present case. But the current presentation, what I'm showing here, is still meaningful, and also I think fairly constructive, because what has to be improved is fairly straightforward once one understands the logic behind the following. So there was a very interesting paper by Domin Sykes in 1957. They investigated poor soil flow, so it's not exactly what we are doing here, but they realized that one can essentially perform a graphical way to retrieve knowledge about the rays of convergence if the limit exists. So for this, one essentially just draws subsequent ratios of Taylor coefficients and plots them against 1/n. And for many problems, I will be a bit more specific for what problems exactly. These ratios settle into a regular behavior and even into a linear behavior at very large orders. And this essentially justifies a linear extrapolation to 1/n going to 0, which of course in the present case implies that you essentially take the n to infinity limit, as also written in this ratio test here. So what's happening on a graphical level here? Maybe let's first look on the complexified time variable, is that there might be somewhere a singularity here on the complex, on the disk of convergence here, that is shaded here in gray. And now the problem is the question whether this limit exists depends crucially also on where the singularity or singularities are located on this disk of convergence. And to be specific, the Dom-Sykes method works if the leading order asymptotic behavior of the velocity would be of the form as given here. So this would be essentially gives you here the location of the singularity that in the specific case has to be on the real-time axis. This is quite crucial. I'll come to this 1 second. And you have a singularity exponent that essentially could be positive, negative, but it cannot be a positive integer. And just like an example of what I actually mean with a singularity, you can actually also see it here. This is like an essentially non-analytic term, what you see here. So suppose that rho, the singularity exponent, is positive, but not an integer, then, and you start taking temporal derivatives of this object, then you would see that at some orders, specifically with this relation, that the derivatives of this object would blow up, which means you cannot represent the function by a converging Taylor series, and it's also not anymore in C infinity. So now I come back to the precise location of the singularity. So let's look at this, because I even put it here in the map in this sketch here. So the singularity has to be somewhere here on the real-time axis, essentially. Why? This has been very nicely demonstrated in a very nice paper. I really like this paper here by Van Dijk, 74. It's a classic, I would say. And essentially, you just look on the Taylor series representation of that model function that supposedly mimics your asymptotic behavior of your original problem. And it is very easy to essentially represent this Taylor series in terms of some generalized binomial coefficient. And when you essentially now just take these binomial coefficient and you take essentially the ratios of subsequent coefficients, and you get then exactly for any n larger than 2 this relationship here. And that basically tells you, okay, if T star is real, then essentially you get a singularity that is really just along the real-time coordinate. And this kind of relationship also gives you explicit instructions how to obtain in a graphical way the 2 unknowns in your problem, because in principle rho and T star are of course unknowns, so one has to first find a way to retrieve them. So having this in mind, the Dom-Sykes method makes I think a lot of sense. So one is now doing the following, or let's demonstrate it on a toy example. So let's think about a completely unrelated problem where you have a function that obviously blows up directly at t equal unity. So it's a very naive example, of course, here. But now do the same as essentially we do with the inviscid burgers. We don't have the exact solution supposedly in the inviscid burgers. Supposedly, of course, we know it by the Lagrangian map. But let's just assume we don't. and we instead only have access to the Taylor series coefficients of the Taylor series representation. It's a very simple all recursive relations you can retrieve from this function here. And what you get is drawn here is precisely the Dom-Sykes plot. So what is shown here as red dots is exactly the ratios of Taylor coefficients, and as promised, they are drawn over 1 over n. So the lowest ones start over here, and the higher you go, I think for this figure I went up to order 78 here, so I don't remember anymore, but fairly high. And you see in the present case, actually they are essentially all aligned on a linear line. So that gives you this very simple linear regression you can draw, and you can retrieve from that precisely the singularity location, which is essentially really just 1 over t star. So it's unity as expected in the present case. And with a few manipulations, you can also retrieve the singularity exponent. And of course, in the present case, you will find that it is -2. Okay, having this in mind, let's go back to our problem. And I will not show you the Dom-Sykes plot for the inviscid burgers because the limit is not existing. So what we have observed is the following: is that when you take these ratios as requested by the Dom-Sykes method, then you get sign swaps. And for that reason, essentially, the limit is not really meaningful. It's not really existing. And one reason why this can be the case, or is usually the case, is that there are somewhere convergence limiting singularities that are not on the real temporal axis, but somewhere in complexified space. And for this, there was a very nice paper also by Mercer and Roberts in 1990 that basically generalized the Dom-Sykes method, and to allow for a pair of complex singularities. And the idea is very similar to what I've just discussed with the Dom-Sykes method. Now, the only kind of change is that now the location of your singularity or singularities is now somewhere in the complex time. And for reasons of basically keeping the problem real, you need to also allow for a complex pair. So essentially, if you are in complex space, you need to have like one singularity on the upper side of the real axis and one on the lower side. Otherwise, you cannot guarantee the realness of your function. And yeah, so then you can essentially just also introduce the singularity exponent as I did for the Dom-Sykes method. And the only other quantities that one has taken account is now that t star, the locations of the singularities, are now essentially have a modulus and also a phase. And I will come to this in a bit more detail, or it will become obvious in the next 2 slides. All these quantities here are in general x dependent, so they depend on the location where you precisely evaluate your velocity later on. It's not really a complication. It's pretty much straightforward to see why this is the case. But let's first begin, or let's finish with the idea of Mercer-Roberts. So instead of now taking just the ratios of un divided by un minus 1, as in the Dom-Sykes method, they came up with a new quantity that essentially is just a combination of suitable Taylor coefficients. And by investigating essentially the limiting behavior for n going to infinity or very large, then you get this relationship. So you get here again 1 over r, which is the modulus of your location of the singularity. You get a singularity exponent, and then in principle you get also higher order corrections, but they are also dependent on the phase. So some of them might be not really relevant, or at least not the dominant ones when you would go to n to infinity. So you get also a similar estimator for the phase. I'm not showing it here. You can see this in our paper, or also in the Mercer-Roberts paper. So that's I will rather show you the results here. And so this is now essentially the mouse or robot plot, if you want. And for the present choice, I've just picked 3 locations in space and evaluate these this estimator Bn. Okay, and what you see is essentially that you get at low Taylor orders still some kind of non-linear behavior. Some here in the present case here some kind of oscillations. But if you go to sufficiently high orders, the linear extrapolation is really justified. You see that essentially you just take a suitable number of Taylor coefficients here, and then you see that you can extrapolate to the origin. Excuse me. And this essentially allows you to give precise knowledge of the rates of convergence and also of the other quantities in your problem. So here it's just shown for 3 spatial locations. If you do this now for the whole space, you get the following. So now I'm doing exactly the same as I showed you in a previous figure, but now for over the whole 1 torus. And you see now that on the top figure, this is the radius of convergence. That is, or the modulus of it, of the singularity location. And what you get are these kind of belly shapes here. So here is crucial. Here it has to go to unity. Because this is essentially for the present choice of initial data, just the time of the first pre-shock. So that's unity in the present case, but then you get a arousal convergence that is lower than unity, that is around 0.663. And on the lower bottom, lower panel, you also see the corresponding phase of the singularity. So everything is defined in here. And you see that the phase actually is pi over 2. And this basically means that the singularity that is essentially sitting, or like has a modulus as given in here, is exactly aligned along the imaginary time axis. So we're dealing here with a problem that is that basically gets singularities or sees singularities that are completely in complexified space, very far away in principle, one might think, from the real time axis. So, but since this is the smallest convergence radius, it also is meaningful to define this as the instance where the Taylor series is essentially absolute convergent. So this Rnf essentially is just taken to be the worst case scenario of your all R's, and in the present case this occurs precisely at plus minus pi over 2. And maybe to get a bit different intuition of the same figure here, you can also actually, sorry, I want to first show you exactly what this means here. So these resonant behavior that we observed in the previous slides are exactly like located here, and what you get is these resonant behavior precisely at a time somewhere around t equal to 0.66, simply because locally you lose convergence of your Taylor series. Now, just as promised, another representation. You can essentially take these 2 figures here and you plot them parametrically over X, and then you can get this kind of I shape where you can also draw the disk of convergence in the present case. And about the Lagrangian theory, I will talk in a second. So these are complementary results. So similar analysis can be done also, of course, for multimode initial conditions. That's shown in our paper. Rahul Pandit gave last week already a very interesting talk where also work with his PhD student Svetya was presented, where they also used these methods for the 1D Hilbert model and also for the axisymmetric incomplete Euler flow. And of course, I speculate that these methods could be applied to many other problems. So, yeah. Let's talk about the singularity theory that we have exploited and developed. So for this, one introduces first the direct Lagrangian map. And the Lagrangian map essentially is really just, you can think about a parametrization of your fluid particles. So basically, you give all fluid particles a specific label that you prescribe at some initial time t = 0, and you essentially track the current position of your fluid particles with the Lagrangian map. That is the current position at time t. And the Lagrangian map is essentially defined through this characteristic equation that defines the velocity in terms of the Lagrangian map. And the inviscid equation has then turns into a very simple acceleration law, or like conservation of acceleration, which has a well-known pre-shock solution. This is essentially just we would call in cosmology like a ballistic motion, essentially, because you essentially just start shooting particles with an initial prescribed velocity, and that's essentially the whole physics, what's happening until the pre-shock occurs. And the pre-shock you can, of course, as many of you know, determine by essentially require the vanishing of the Jacobian determinant that is defined in the present case like this. And now let's use this kind of basic picture to locate the singularities that I showed you before. For this, we know already that there's something happening in complex space. So it is a necessity to also complexify the temporal variable and the Lagrangian space variable. And then essentially just look for the vanishing of the Jacobian, not in terms of, let's look at T star essentially, but search basically for the Lagrangian roots that that satisfy these this condition here. And it is quite easy to see that if you essentially draw these roots over like early times, I mean, here again, this would be the pre-shock location here at t = unity. And you see that the imaginary part of the Lagrangian roots is non-vanishing before. That essentially means that both Lagrangian roots are somewhere in complexified spatial space. And as time progresses, these singularities, or these roots essentially of the Jacobian, are coming closer and closer to the real-time axis until they become real and the imaginary part is vanishing again. So now the essential idea of the Lagrangian theory is now as follows. If these vanishing or the roots, Lagrangian roots, can cause any trouble in Eulerian coordinates, then it is also a necessary condition that the current position, the Eulerian position, has to basically, something has to happen on the real valued current position, because before it is in complexified space, it should not cause any problem for the time Taylor series. But the time Taylor series in the present case is evaluated at real valued Eulerian positions. And essentially to check for what happens with these Lagrangian roots in Eulerian space, one simply has to require that the imaginary part of the current position at the Lagrangian roots has to vanish. And then one can basically draw exactly this as a temporal evolution here. And for this, I also essentially, these are the phases that I just rendered pick of your temporal time axis. And you basically see that the roots of this problem, basically when the imaginary part of this object vanishes, is dependent on the phase of your time coordinate, your complex time. And this is also shown here in this figure here. It's actually also an animation. So you see here, before I start animation, that it is just starting to touch essentially here the real axis. So the imaginary part of the current position is vanishing exactly at this time. But at early times, just here's the time written, you see that they are somewhere in complex space. And then just when it essentially hits this critical time of the convergence of this R infinite, infimum that I showed you earlier, you see that they really appear at the current location, and this causes essentially the time Taylor series in Eulerian coordinates to lose analyticity. Okay, now 2 ways to express Tigers. I'm a little bit low in time, so I need to speed up a bit here. So one idea is essentially adapted technique. Chomredi, the host of the present session, was involved heavily in this project. The idea essentially is very similar, like in this Murugan paper, where they basically looked at Galerkin truncations. In the present case, we don't have really a Galerkin truncation, but we have a Taylor truncation for the arguments that I showed you before. And the idea is essentially to look in a certain shell in Fourier space and remove certain Fourier modes and see what's happening. And this I show essentially here in terms of sigma, which I define as an integrated error. Basically, I just take the difference of the Taylor truncation of the velocity and apply also like this purging operator here, so that really just selects certain Fourier modes and filters some of them out. And the difference essentially is taken with respect to the exact Lagrangian coordinate solution U0 of A. And when you integrate over this, then you get this kind of nice figure where you see at early times, this integrated error is really just declining very fast until it levels off essentially at machine precision. But now you go to later times, you see that first of all, the integrated errors are getting, well, they still decay, but not as quickly as at early times. This is kind of like a feature what you expect of a Taylor series if you come close to the convergence range, maximum convergence range. You see then suddenly also like a burst of integrated error that is precisely essentially now telling you, okay, if I now have, for example, 70 Taylor series coefficients, this is these solid lines here, and now I essentially allow the Fourier modes beyond 40 to participate in your solution, then you actually get a large error that really blows up. And this error is essentially what is this related to this Tyger phenomena. And if you go to later times, it really blows up and completely spoils your solution. But now if you instead just say, okay, let's cut off all this chunk that causes the errors. Essentially, you just take this solution here up to this moment, and you chop off all Fourier modes that are from here up to here, and similar for the other times. So this is kind of time dependent, this operation. And then you get this kind of figure. I mean, this is now very close to pre-shock. You see some errors, but still, if I would show you this without any purging, you would see nothing here. So the purging works extremely well here to recover the solution as good as possible. And if good as possible, I mean essentially in Eulerian coordinates, of course, not in Lagrangian coordinates, which is the exact solution. So it, of course, works also well for multimode initial conditions that I show here. And one follow-up question that I find interesting is how does this purging method actually relate to renormalization techniques? This is something to keep in mind, maybe. I don't have an answer exactly to that at this stage. Now the opposite idea. How's time? Okay, I need to speed up. So let's quickly sketch the opposite idea. What I mean with opposite essentially is, instead of discarding Fourier modes, let's see if there's a mode, like a way to actually add certain Fourier modes in a very efficient way, and see if this improves your solution at times when the Taylor series would lose convergence. So for this, one can simply integrate Burger's equation in time, and then you essentially get, in the smooth case, just this very simple explicit solution. And what you can do now is, let's just say, okay, the right-hand side, let's see it as some kind of generating function, and you say, okay, let's take it as an approximation. I take a Taylor series truncated velocity, where this capital N is just the Taylor truncation here. And now let's plug in this equation in this approximation. Then what you get is essentially this equation here. So you get like some kind of approximation of another velocity that is now essentially a function of your Taylor series truncated velocity. And of course, you can continue this all the way along. You can use this as the input for the next iteration. And you basically take this solution here and you iterate it here, and you get higher orders and higher orders very quickly. So this is much more efficient in a computational way than a Taylor series approach, because whenever you do these kind of iterations, you roughly double the number of Taylor coefficients. So this is very efficient in filling up essentially the whole Fourier space with Fourier modes, much more efficient than what you get at Taylor series orders. And here I show you essentially just a solution of the velocity, and I use here essentially the fourth iteration in this Duhamel-inspired principle, what I'm doing here. And you see that it actually takes only as the input the blue line, and I'm showing you also here the difference. So the difference is here that at this time, 0.7, you actually have already developed some resonant behavior, and I nonetheless plug that solution here in the input in this bootstrapping procedure that is then leading to this solution in dark green. And you see that whenever I do this kind of bootstrapping, I reduce the amplitude of these resonances here by quite a lot. So it works certainly, and I also show you here essentially that it also restores the violation of energy conservation, something that you would also expect, because once the Taylor series loses convergence, you would expect that also that energy is not conserved anymore. You see, this is just like an error essentially of the energy conservation that I find like this, and capital U is just one of these solutions. And you see, if I don't do this kind of UV completion, then you get this kind of drastically increasing error in the energy conservation. But if I now go here to the right, you see the more iterative procedures I include, the lesser the errors get. So in this direction, the errors are declining, but also, I mean, if you compare it in comparison to this and this, so it's a good trend in principle. It restores the energy conservation in a good way. And now the last few minutes, it's just 2 or 3 slides. I want to also give you like a context of what we just discussed, of a very interesting problem in cosmological structure formation. So this might now seem to be like, wait, this is now a completely different talk. Suddenly, no, it isn't. This is my point I want to make here. So the evolution equation for the cosmological problem, they look vastly different on first sight. So you have your fluid velocity that is now essentially coupled to a gravitational potential, and the gravitational potential is governed by a Poisson equation, and you have a law that basically tells you something about mass conservation. So this looks completely different than the inviscid equation that I showed you before. But now, if you take this 3D description in one space dimension, and you use suitable boundary conditions, I can give you details to this, what exactly one has to do, then momentum conservation exactly reduces to the inviscid case. So what I wanted to raise here is that the inviscid actually is highly related to a problem that leads to this kind of cosmic structures that you see here in the background of this animation, if it's not too dark for you. And so this is, I find it very interesting, basically because what I showed you before directly applies to the 1D case also in cosmology. So now in cosmology, we have a coupling between the fluid velocity of dark matter and its fluid density. And by the same methods that I just outlined before, one can essentially get similar recursive relations and also retrieve like Taylor truncations of the density. And what one gets is essentially the same problem as I showed you before, but now also you get the density that gets these kind of, well, in the early times, it essentially is converging. But at later times, the Taylor series for the density gets this huge resonant behavior, as I showed you before. But now, for example, if I apply the purging, then I essentially recover the Eulerian coordinate solution or the exact solution to a very good extent. So the exact solution here is, again, the Lagrangian coordinate solution that applies, of course, also in the cosmological case. And you get also, of course, the same eye of the Tyger figure that I showed you before. Okay, last three slides, but I'm very quick. So beyond 1D, you need to do something a bit better than just using Eulerian coordinates. The best solutions that are widely also used in cosmology are Lagrangian coordinate solution. So I show you here just some figures, essentially, what you can do here with 3D solutions for random initial conditions. So you take the particle trajectory, and now you essentially do a very similar Taylor series, but now by means of the Lagrangian map, essentially here. And because we use random initial conditions, we also need to use like a numerical setup. So you use collocation points, and you need to idealize your calculations, of course. And what you get essentially is that these solutions for the cosmological problem, they are converging up to the time of shell crossing. Shell crossing is just the time when the density goes to infinity. This might come to a shock for people who are not familiar with the cosmological problem, but this is a very known feature of these equations, that there is a blow up essentially in the density, and this occurs at one certain space location. And this space location, you can also show the Dom-Sykes plot, and you see that there actually is some linear behavior. So the asymptotic analysis actually is easier in Lagrangian coordinates and for the present problem, much easier than in Eulerian coordinates, where you have complex time singularities. Also here you have just singularities that are essentially along the real-time axis. So this makes the problem very nice and tractable. And so the if you now look, for example, at the L2 norm of this displacement or these map coefficients here that I showed you here, you see they are turning into a linear behavior at large Taylor orders. This is just different resolution on the spatial grid here and different initial conditions. This WDM, CDM, not so interesting for you. It's just initial conditions choice. But what you see in all cases is that the L2 norm of the map and actually also the entries of the corresponding Jacobian matrix on their own behave asymptotically as this function here. And this is exactly why we can actually use also the Dom-Sykes method. So the circle of logic kind of closes here maybe. But one very interesting feature is that T star is not exactly the time of shell crossing in general. So it could be, but for this you need very fine-tuned initial conditions to achieve that. But what we observe is essentially in the Cosmo case that the shell crossing singularity is somewhere within the disk of convergence, whereas the T star that is essentially marking the disk of convergence is beyond. That's very interesting because it gives you certain nice features how to progress in time after the first shell crossing. Because what's happening here in phase space, you just look at the velocity over the current position in time, you get precisely this kind of point where the solution will start to bifurcate, and you need to do something about this. And this can be done essentially by using a Vlasov-Poisson description. So three important lessons essentially from this Cosmo case is, well, we actually have it's quite a thankful relationship because we can actually solve the fluid equations in a Cosmo case really up to the moment when they cease to be valid in a single time step, no multi-time stepping involved. It's really just an expansion around the initial data essentially, and you get retrieved the whole solution, and it's converging up to the moment of shell crossing and even slightly beyond when it ceases to be physically meaningful. What I mean with that is once you basically hit shell crossing, you come into a regime where you obviously also generate velocity dispersion. So you get here current locations where you have multiple fluid streams in the Cosmo case, and that of course is like a source of generating velocity dispersion and other higher order kinetic moments of your hierarchy in the Boltzmann hierarchy. And so one has to somehow swap to a different description that is precisely the Vlasov-Poisson description. I will not come into much detail today. This is another talk basically, but there's a review I recently published there on this, so I can recommend that, or some other papers if you like. And so this is another very interesting lecture that basically you can swap smoothly between the fluid limit and the Vlasov limit. And nonetheless, you will have also lots of time analyticity, as we also wrote down in this paper with Uriel, Frisch, and Oliver Hahn recently. Another thing is, this is the last point of the day. I'm sorry, I'm slightly over time already. Speed of convergence of the Taylor series is unfortunately not very fast. So fast, the speed of convergence depends on the initial data in general, what we observed. But for some applications, you want to get fast predictions, especially when you want to use these kind of theoretical predictions and use some kind of hybrid approaches where you pair it in a way with some simulation techniques. So this is very crucial to get fast and reliable predictions. And one idea of this is essentially first put basically the finger where it hurts. This essentially is a Lagrangian coordinate solution in 3D, a fairly simple one, where we actually have an exact analytic solution that goes back to Tolman in 1934. And this is a very tough, I think the toughest problem for the time Taylor series, because it is very slowly converging, as you can also see here. So this is essentially the Taylor truncated current position of your particles on the spherical shell. And you see that the exact solution here, this is the one of Tolman, you get this kind of oscillating behavior. This is not at all recovered here in the present case. The convergence is very slow. And by essentially also exploiting like kind of the symmetry of the problem, you can essentially, if the time goes this way, you have essentially a model of an overdense region, essentially a spherical overdense region somewhere in the universe, and it just collapses. This essentially was shown here on the right side. And the left side is the opposite case. It's an underdense region, so it's somewhat has a lower density locally than everywhere else in the universe. And that is this kind of other evolution, what we see here. So you see that these truncations are slowly converging, very slowly, and also they show this kind of pathological behavior once convergence is lost. So there are two methods that we tested. And they actually, they are really just exploiting essentially the non-analytic features that I showed you also in this talk all over the place. So one is essentially a UV completion that basically is just it's quite simple idea, I would say. So you basically, once you know the analytic structure or the non-analytic structure at very high Taylor orders, you simply take a low order truncation of your current of your map of your particle positions, and add this non-analytic term. There are, of course, a little technical details that I leave out here, but this is very easy to rectify. But this is the essence. You essentially take a truncation, Taylor order truncation, low order, and then you just add the non-analytic term that encapsulates the leading order asymptotic behavior, and you get a vastly improved theoretic prediction by very low cost. Basically, it's very simply to generate these solutions. Another one is it's kind of a complementary approach to the UV completion. It is the implementation is somewhat different because you start essentially with reformulating the problem and look for the RG flow equation and look for stable fixed point solutions. And in essence, you retrieve from this RG approach exactly the same kind of non-analytic term as from the UV completion, but you recover it essentially, it spits out in the system. You don't need to do any kind of Domain-Sykes analysis. You just get it from the RG approach straight away. It's very interesting. And they are kind of competitive, I would say. I mean, one approach works a bit better on the left side, the other one works better on the right side, but they both are actually quite efficient approaches. and they can be also generalized to more realistic initial conditions. So this is where I now stop here. Sorry for the slide over time, and I can take now some questions if there are any.
Thanks, Cornelius. Questions? Yeah. Okay. So maybe I can ask a quick question and then we can go to the comment. Yeah. Cornelius, just a couple of quick questions. So in the UV padding approach that you'll implement, how do you choose the time scales, the time intervals in which you pad and add the modes?
You talk about the iterative UV completion, right?
Yeah.
So here we also just used a single time step at this stage. So one can of course try to do like a multi-time stepping procedure here, but at this stage it is just really introducing the technique. We wanted to see what can we do, what is the best we can achieve within a single time step. So this is more like a theoretical game, I would say. Let's see what is the maximum output we can retrieve from this technique. But yeah, of course, you're right. In principle, one requires follow-up studies to check what how this could be implemented in an efficient way if one wants to implement this. I also gave some interesting points about this here in the conclusions. So basically, can one use this kind of iterative UV completion? Well, where also, as geometry says, one has to take care basically the temporal spacing in a simulation, for example, and but then essentially use this UV completion for a simplified subgrid scale modeling. And for this, one should also remember that or recall at least what we found in our paper. This method does not really require a Taylor series input. It's really kind of agnostic on what exactly is needed in this iterative procedure. So there are lots of issues that have not been really solved. We have not tried to do so because there are so many other things we are working right now on that are a bit more on the to-do list right now, but this would be, of course, highly exciting and interesting to investigate such approaches here. Yeah.
Other quick questions. So, because the times that you showed, which were quite short compared to the time of the pre-shock, does this UV iterative scheme lead to artificial dissipation of some form? Well, we have pre-shock. In the inviscid problem, of course, yeah.
Yes, so it is true. In comparison to what we show with the purging strategy, the purging seems to be more efficient, also at later times than this iterative UV completion. But my thinking is the following: when you do the purging, you essentially discard information in the UV regime. Right. So when you do that, you essentially make the solution to some extent less accurate, at least in the very high K regime. So if you now would combine this iterative UV completion in the multi-time stepping process, where you basically add information in the UV, I would expect that it would be competitive, or I don't know. I can only speculate what would be the performance here. But one has to investigate exactly what happens here in a more realistic setup. So at this stage, we have seen also here essentially with the energies. If you go to later times, you see that the errors in the energy conservation are clearly still fairly low. But if you compare it the times here in the last iteration here, you see they increase from 10 to the -6 at early times to 10 to the -3. So you see clearly that this UV completion is vastly dependent on choosing a good time stepping. So if your time step is too large, essentially if you have too many Tigers already in your solution, this UV completion will not cure your problem. So you need to basically find a way to basically swap the UV completion or like the time stepping as soon as you have too many Tigers, rectify and perform UV completion so that the method has some chance to cure the solution from the Tigers. This is at least my kind of current thinking of the situation, what one could or should do. Yeah.
Great, thanks. Any other quick question, and then we can go for a comment. You had a question? Okay. Okay, so maybe there's a comment here.
Yeah, I don't know, you can treat it as a comment or a question, but anyway, you refer to the dark matter solution, and see, there are two physics involved. One is the fluid physics, the other one is the physics of matter, or compressibility, so where density is involved. And the Tyger purging, that depends on what frequencies you actually introduce and in what phase space. And so there is, of course, the cross coupling between the two physics, and the mechanism of energy dissipation depends on what modes you are introducing and at what phase, and also on how the energy is dissipated, whether it is the UV, I mean the fluid physics and the coupling which actually dissipates energy, or energy gets dissipated in the matter, or as a viscous dissipation. So I don't know whether.
Yes, I mean, I think I fully agree with all of the comments. But I would see many of the comments are not really an issue, because if you, I mean, one of the major issue, of course, is that what exactly is UV in the cosmological sense is drastically dependent also on the choice of initial data. So if initial data of your, in the Cosmo case, is typically assumed to be a Gaussian, and if you look at the power spectrum, you also see that the power spectrum has a very specific shape, that it basically is like a bell. So it decays off quite quickly in the large K regime. And that is actually quite a blessing, I would say, because it you can just from these considerations you can see that UV effects should not play a drastic role. They certainly will play a role in cosmology, but not as drastic as they could play in other fluid problems. The other comment I want to make about the particle nature or particle physics approach of dark matter. Yeah, of course, right. We are mixing here a couple of issues in one bag. So when we basically use this fluid description, or more general a kinetic description based on the Vlasov-Poisson equations, that essentially is this here is just a reduction of the Vlasov-Poisson equation that is valid at early times. We assume that dark matter behaves as a continuous fluid and also as a collisionless fluid. So from the particle point of view, this is first of all an approximation, of course, right? Because collisionless and also essentially very cold, or basically exactly cold fluid, means that it does have not initially any thermal momentum contribution. So the spectrum, the velocity spectrum, is really just of kinetic origin, not thermal. This is essentially the assumptions in this cold dark matter model that we use in cosmology all over the place. Yeah. Now, particle physics will tell you this is an approximation, and you might expect some corrections if you go to certain scales and times. This might be true, but we also know from a host of observables in cosmology that these approximations that I think are not really approximations, but rather limiting processes. So it's a limiting process to take the code limit and so on. They actually produce excellent results in comparison to what we observe. Okay, so this vastly simplified limiting model that we investigate actually is fully meaningful, at least if we look at the current observables in cosmology. So it is, of course, somewhat an approximation from the particle physics point of view, but the scales that we're interested in, which is the like very large cosmological scales, this is way larger than galactic scales that we are looking here, then these limiting or approximating features are actually perfectly justified, because any reasonable dark matter candidate from particle physics will have a mass that is way lower than the mass of a Milky Way. I mean, it will be in the electron volt regime, maybe giga electron volt regime or sub electron. So it could be anything basically, but it will the mass of the dark matter particles will not be much larger than the weight of a typical black hole, because if you think about primary black holes, for example, yeah. So there are many aspects to your comments, and not really a question. So I kind of agree, but on the scales that we are interested in, I think we have a good understanding what to expect from UV effects, and also what to expect from particle physics.
On that note of agreement, Cornelius, let's thank you once again, because we have to break for lunch and not purge away. Thanks, Cornelius, and see you soon.
Thank you.
Take care.
Thank you.